So a computer's physical memory is a hardware structure that consists of a linear sequence of words that hold a program while it's executing. So a word is a fixed size unit of data. And so the physical address will then be an integer in the range 0 and -1 that locates a word in a physical memory of size n. And so the address itself consists of a fixed number of bits. How do we know how many bits? So a memory that has a size n requires an address of size k bits where n equal to k. So for instance, if our memory is of size 8, so our memory can hold 8 words, then to represent their addresses, we are going to need 3 bits, right? And so if we have an address space of 1024 words, right? So if the size n is equal to 1024, then each address will occupy k bits, okay, where n equal to k. So in this scenario, n equal to 10. Therefore, any address will have to occupy 10 bits. And so during the development of a code or of a program, the starting physical address of that program is unknown, and then to facilitate the program development and to be able to share physical memory, people have invented the concept of a virtual or logical address space. So a logical address space is an sort of an abstraction of the physical memory, which again consists of a sequence of virtual memory locations in the range 0 to m-1, right? Just like the physical address, where m now is the size of the logical address space. So before execution, a logical address space has to be mapped into physical memory, and then the program will be copied into the corresponding location in memory. So we talked previously about contiguous memory allocation, where the physical address space of a process had to be contiguous. Now we introduce a new memory allocation strategy called paging. So with this scheme, a process is permitted, the process physical address space now is permitted to be non-contiguous. So paging divides both the logical address space of a process and the physical memory into equal size partitions, okay? And then any logical partition has to be mapped to any empty available physical partition, okay? So we're not going to be searching for holes, variable size holes anymore, and then we're not going to have external fragmentation, okay? However, paging suffers from internal fragmentation, as we will see next. And so paging divides the physical memory into fixed size blocks that we call frame, okay? And then we divide the logical address space into same size blocks that we call pages. And then we have to keep track of all the free frames that we have in memory. And then to run a program of size n pages, we just need to find n free frames to map into and to load our program. And so to do the mapping and to keep track of the mapping, we need a data structure called the page table, which is an array that keeps track of which pages of a given logical address space resides in which frame. So as you can see in this example, in the page table, we say that the page number 0 is actually residing in frame number 1. So if we go to physical memory and find frame number 1, we're going to find page 0 in there. And then it also says that the page number 3 actually is residing in frame number 7. If we go to frame number 7, we're going to find page 3. And so as you can see here with paging, one process is divided into multiple pages, and then those pages, they don't have to be mapped into one single variable size chunk in the physical memory, but instead every page can go into any free frame that is available in memory. They don't have to be contiguous. And so for each process, we have the pages that are numbered consecutively, starting with page number 0, 1, 2, and so on, right? When we're talking about pages, we're talking about the logical space. But once we map it into frames, then the frames, as we just saw, they do not have to be consecutively numbered, starting with it can start with any frame number. It does not have to be 0, okay? So whatever free frame we find, we can just allocate our page to it. So it can be frame 7, frame 9, frame 10, and so on, okay? Also bear in mind that the operating system does not have a single page table for all processes. Instead, we have a single page table for each logical space. And so every process will have its own logical space. Therefore, it will have its own page table. Okay. And now let's talk about the address translation scheme. Let's talk in details about the addresses themselves. So once an address is generated by a CPU, the address actually has two parts. The first part is the page number P, and the second part is the offset W. So P represents the number of the page itself. Let's say this is page 1. And then the offset, because each page will have multiple words in it depending on the size of the page, and then the offset is what enables us to navigate inside the same page. Now, if my address space is of size 32, then I will need 5 bits to address each of those 32 bits, right? And then the addresses will start with 00000 to 11111, right? And this is a total of 32 words. Again, a word is a basic unit of data. So if I have now a space of size 32 words, and we said we're going to need 5 bits to address each of those words, then if I decide to divide my space into pages of size 8, so that's my choice. If I decide that each page will have a size 8, which means it will contain 8 words, okay, then automatically I will need 3 bits to address each one of those 8 bits, right? So starting with 000 to 111. So from word 0 to word 7, right? So the 3 here is what specifies the offset that we talked about, right? So remember, we need the page number. Let's say this is page number 0. And then we need the offset to address each word inside that specific page. Okay. So in this scenario, we just found the K, which is 3 bits, which represents the offset. Then automatically, once we have defined that we have 3 bits for the offset, then the remaining 2 bits, right, 5 minus 3 is 2, will represent the page number, okay? And then the total number of pages will be equal to 2 to n minus k, which is 2 to 5 minus 3, which is 4 pages, okay? So I started with 32 words, right? Words. And then I decided that I want to create, I want to divide my space into pages of size 8 words. Then automatically I will end up with total of 4 pages that each has a size of 8 words. Okay, and so in terms of bits, since the total address space requires 5 bits and I will need 3 bits for the offset, automatically I will need the remaining 2 bits for the page number. So therefore my logical address space will look as the following. So these 2 bits are for the page number. So 00 will indicate the page number 0, for instance, right? And 11 will indicate P3, which is the last page. So in this scenario, we have page 0, page 1, page 2, and page 3, right? So 11 is 2 to 0 plus 2 to 1. So this is page 3. And 00 is 2 to 0 plus 2 to 0, and this is 0, right? So then I have 4 pages, and each has 8 words inside, exactly 8 words. And therefore, to address each one of them, I will need an offset that has 3 bits. Now, if I decided to divide my logical space differently, which means I will choose a different page size. So in the first example, we choose a page size of 8. Now, what if I want a page size of 4? So every page will just have 4 words, right? So the n does not change because the total space size does not change. So all I have to redefine is the offset, okay? So since the page size is 4, in that case, k in this scenario will be equal to 2. So I will need 2 bits for the offset. Therefore, for the page number, I will need 5 minus 2, which is 3 bits to represent the page number, which makes sense, right? Therefore, the total number of pages that I will end up with is 2 to 5 minus 2, which is 2 to 3, which is 8 pages now, right? So in the first example, if we divided the space into pages of size 8, I ended up with 4 pages. Now, if I divide them into pages of size 4, I will end up with more pages automatically. In this case, I will end up with 8 pages since the total is 32 words, okay? Okay, now for the physical space, we have to, as we said, the frame size has to be equal to the page size, right? Since in the previous example, we decided to have a page size of 4, then we have to divide the physical space similarly and have a frame size of 4 words. So if we assume that we have a physical space of size 64, then I will have a total of 6 bits to address all of the 64 words. And then as we said, if my frame size is 4, then I will need 2 bits for the offset. And then automatically 6 minus 2, I will need 4 bits for the frame number. And then the total number of frames, we're going to have 6 minus 4. N is 6 and K is 4. So we're going to have 2, 2, so K here is 2, the offset, okay, and then 6 minus 2, so 2, 2, 4, which is 16. So we're gonna end up with 16 frames in the physical memory, right? So you can see the logical space here, and then the which will consist, as we said, of 8 pages of size 4. And similarly, if we have a physical space of size 64, then we're going to end up with 16 pages again, with 16 frames, right, with size 4. Okay, so in the logical space we call them pages, in the physical space we call them frames, and the frame size has to be equal to the page size. But the space, the spaces themselves can have different sizes. For instance, in this example, the physical space had a size of 64 words, whereas the logical space that we started was that had a size of 32 words. Okay, so the sizes of the two spaces can be different. However, the sizes of the page and frame has to be the same. Why? Because we're mapping every page into an empty frame. And so if we are mapping page P0 into frame F1, then the logical address of P0, we're going to take the page number part, which is 000, and we will map it to the frame number, which is in this case 0001, right? And then the offset will be copied and remain the same. So the address 00000 will be mapped to 000100, and then the address 00001 will be mapped to the address 00101, right? And so on until we finish all the 4 words. So the offset itself will be copied and remain the same. Again, the offset enables us to navigate inside each word in one frame or in one page. Okay. And so what the size of W will determine is, since we are talking about physical memory here, so the size of the offset will determine how many words per frame we have. Now, what about P? So what does P represent? So P mainly represents how many pages we have in the logical address space, right? So P represents the page number, okay? So it does not represent the number of words inside one page, because that's the job of the offset, okay? Again, the size of F will represent the number of frames that we have in the physical space, right? As you see in this example, a F of size 4 bits will give us 16 total frames. And so if we have an address space with a address size of 16 bits, right? So in this scenario, our N is equal to 16. And then if the page size is 512 words, so 512 means our K will be 9, right? So 2 to 9 equals 512. And then the question asks about how many pages. So the number of pages is 2 to n minus k, which means 2 to 16 minus 9, which is 2 to 7 total pages. And so we said that the paging memory allocation strategy does not suffer from external fragmentation like contiguous allocation, but it does suffer from internal fragmentation. So if we have a page size of 2048 bytes and the process size is this, then if we divide this by this, we're going to need 35 pages plus an extra 1086 bytes. We still need to allocate 36 frames. Therefore, we're going to lose 962 bytes to internal fragmentation. That's a wasted storage. So if an address consists of 5 bits for the page number, right? So if we have page number with 5 bits, and if we have the offset W with 4 bits, then the number of pages will be how much? So automatically we're going to look at the offset, right? We're going to look at the page number. So if we have 5 bits for the page number, then we're going to have 2 to 5 number of pages, which is 32. You can also again think of it as 2 to n minus k. So the n here is 5 plus 4, so 2 to 9 minus 4, which is 2 to 5. The page size now is what? Again, what defines the page size is the offset itself. So if we have 4 bits for the offset, then the page size will be 2 to 4, which is 16. What this address represents in binary based on this description. So we are going to have 4 bits for the offset. So 1, 2, 3, 4. So this is the offset, and the remaining bits are for the page number. Therefore, we need 3 for the offset. So both of them are 3, right? So 2 to 0 plus 2 to 1. So this is 3. And then which one of these, so basically not this one. So which one of these represent number 2? So again, this is 2 to 0. Which is in this case 0, and this is 2 to 1. So this address is 2. So this is the correct representation in binary. And so if you have a logical address 3.5, and we know it is mapped to the physical address 4.5, this means page number 3 is mapped to frame number 4. Therefore, if you're looking at the page table, then you're going to find that index number 3, it's going to have frame number 4, okay? So with the above mapping, the starting physical address of the frame will be automatically, since we're talking about frame 4, then the starting address will be 40. So again, what is this? This is the 0 is the offset.